with the structure and dynamics of the atmosphere. It has three different interdisciplinary fields, which are climatology, meteorology, and aeronomy. We are interested in aeronomy because it is concerned about studying the upper atmospheric layers. The atmospheric layers of the atmospheric layers are, as you can see, 5 different atmospheric layers, which are the innermost one, the troposphere and the stratosphere. Since they are low in altitude, we have many studies about them, and they are where most of the weather occurs. And the upper atmosphere, starting from the mesosphere until the exosphere, it is much higher, and so we have little studies about them, but it is important to study these atmospheric layers because they enable us to make future predictions about the climate change, and it is because they affect matters concerning the ecosystem and the safety of the occupants on Earth. And it was found through study that there is a phenomenon taking place right now called the shrinkage of the atmospheric layers. This shrinkage of the atmospheric layers would make it much more easier for space debris to enter our ecosystem, making it much more, making it unsafe for occupants on Earth. So it means the necessity for studying these upper atmospheric layers. Now I leave you with Mohammed on the space axis.
Now, going for the importance of space. Space plays an important role in many aspects in our lives. Television, communication, navigation, and security control systems that we rely on nowadays on our daily basis, like GPS and mobile phone calls that we can't do without them. Also, television innovation by products same like CAT scan and mobile phone cameras that we rely on nowadays. Also, it encourages the youth for STEM fields, which is science, technology, engineering, and mathematics field. But now, how to reach space? Space can be reached via 3 different flights: planetary flights, orbital flights, and suborbital flights. Let's start up first with the planetary flights, which are the type of flights that requires planetary velocity in order to reach other planets if there is a need to conduct some experiments there and to stay for such a long time. Going for the orbital flights, which are the flights that require to reach an orbital velocity in order to reach a predefined orbit if there is a need to conduct some experiments there, and it's basically for communication and navigation reasons. Going for the cheapest and most affordable way to reach space, which is via the suborbital flights. They are the type of flights that requires a velocity less than an orbital velocity in order to go in a predefined trajectory and return back to Earth after conducting some microgravity experiments and atmospheric experiments there. Now, the problem that we can access the space but from foreign countries. We cannot access the space locally from the Gulf. That's why there's a problem. They put us in their time frame, in their time schedule, and they put their flights in a priority over our flights. Now I leave you with Isa.
Now, after identifying the problem, I'll be talking about the current solutions. The current solution to access space is to use services provided from foreign countries that offers orbital, suborbital, and planetary flights. Currently, Kuwait and the Gulf region are totally relying on this type of companies that provides an access to space and launch payloads there. For example, the UAE used the Japanese JAXA company to launch the Hope probe to the Mars planet using an orbital rocket called H2A, and this launch costed them $90 million. Another example is that Kuwait University used the SpaceX company to launch Kuwait satellite to the orbit by an orbital rocket called Falcon 9, and its cost was $330,000. Moving on with the current solutions to conduct upper atmospheric studies, there are 2 solutions to conduct upper atmospheric studies. The first one is to use a sounding rocket, to launch a sounding rocket, such as the Black Prime rocket, which was developed and launched by NASA, and its cost was about $0.1 to $3 million. The other solution to conduct upper atmospheric studies is to use satellites, such as the GOES-18 satellite shown here. It was developed by the NOAA company, which is the National Oceanic and Atmospheric Administration, and unfortunately its price is unknown. Moving on with more examples of companies that provide access to space. There are many companies that provide access to space, but it can be shown here some of them. For example, we have Aerospace Center. It is a Norwegian company with a suborbital flight. It lands payload with a cost of $44,500 per kilogram of payload. Another example for an orbital company, which is SpaceX, it launches a payload to the space with a cost of $330,000 per kilogram of payload. Now moving on with the possible customers and their interest. There are many customers. You can see here the Planet Lab company. They are interested in buying atmospheric data to increase their database. The NOA, as I said now, they are interested in gathering data on the upper atmosphere. And the NASCOM company, National Aerospace Service Company, they are interested in providing space access to their new launch complex, which is called Itlaq, located in Oman. Now we live in Nasr.
Thank you. So after the thorough research in both space and the atmosphere, we see a need to accelerate space and its industry in the Gulf and the Arab region, and also to address climate change and global warming. So the goal of this project is to access space locally from the Arab world and Kuwait, and also a method to conduct upper atmospheric studies. This will be done by developing a vehicle that is capable of reaching both space and the upper atmosphere. So the solution to this was to develop a rocket. This rocket is composed of various sections that work in parallel together. We have the first section, the nose cone, the avionic bay, airframe, payload, engine, and nozzle. They work together to reach altitude and to succeed in the intended mission of the rocket. So initially, before designing any component, we started with a flight analysis. Through this flight analysis, we can gain the necessary criteria and values that are necessary to design, such as thrust force, weight, and drag. We started with a rocket's equation of motion that took into account the various forces on the rocket, and also takes into account the variation of density, pressure, and the mass of the rocket as it ascends in altitude towards space. The code used was provided by the KSR team through engineer Simon Faith, and also through the code we can get the engine specifications, such as the amount of fuel and the nozzle specs that would aid in selecting the engine. After various iterations of the flight analysis, we got these figures here. These figures take into account the parachute ejection altitude, and you can see that the max altitude occurs at 105 kilometers, which means that the rocket was successful in reaching space. And after that, the descent, you can see that with time, it becomes slower and less steep. This is because the parachute is ejected. And for the velocity, we reached a max velocity of 1,260, which is around Mach 3.6. For the acceleration, we got a max acceleration of 4 Gs, which is 4 times the acceleration of gravity of Earth. And the max drag force, you can see the first peak is 2,253 newtons. The second peak is the ejection altitude of the parachute. And now for the rocket engine, we selected a solid rocket engine based on neoprene, aluminum, and ammonium chloride. The choice was due to the ease of manufacturing and less complexity in comparison with other engines such as the hybrid and liquid. And the engine would be acquired locally from the KSR team. The total propellant mass was 184.6 kilograms, and the thrust produced by the engine would be 8.73 kilonewtons. For the first designed component of the rocket, the nose cone, we selected the von Karman profile from various profiles due to its aerodynamic superiority, and it was designed to be made out of 2 parts, a top part of aluminum and a lower part of PLA for mass conservation purposes. It houses the recovery system and acts as a drag reduction component. So the design was based on various studies. The first study was an aerodynamic study based on Council that used the HIMAC interface flow module. And through it we tested 6 different profiles, conical shapes profiles with varying fillets, and the von Karman profile. And as expected, we can see that the best aerodynamic performance goes to the von Karman due to the least coefficient of drag values. So after that, we did a couple of tests to check whether the tip of the nose cone would melt due to aerodynamic heating. And we did this test because through the aerodynamic analysis, we got a max temperature of 1,400 Celsius, and this might melt the tip of the nose cone. So this experiment used an oxyacetylene torch on a natural flame that goes up to 3,300 or 200 Celsius. And we tested two tips, one which is fillet and one which is just sharp. So for the sharp fillet, it starts to melt at 10 seconds, and it was neglected. We went ahead and used a filleted nose cone, and that's sustained the temperatures up to 25 seconds, and it was chosen for the rocket. After that, we did a structural test to check whether the PLA would take the forces. It was a static test based on putting plates on top of the PLA part, and it sustained the max drag force of 2,200. By simulation, it's around 240 kilogram of weight. And now I'll leave you with Hamad to talk about it.
Going for the airframe. As you can see, the airframe consists of 3 radial threaded rods, aluminum plates in between, with air covers surrounding them. Also bolts that connect the air covers to the aluminum plates. We conducted a free body diagram. We conducted a free body diagram of the whole rocket to see what type of loads that the rocket will face during the flight. It results that the airframe will be squeezed between two normal forces in top and bottom, and it was calculated to equals 5,943 newtons, and we based our stress analysis based on this value. We did 4 types of stress analysis: buckling, compression, shear, and bending stress analysis. We did a buckling and compression stress analysis via COMSOL, and we did a shear and bending stress analysis via MATLAB. Stress analysis were done and safety factors were calculated to prove that the design will take the load. It results that having 3 M12 stainless steel threaded rods with 8 mm thick aluminum plates with 3 mm thick aluminum air covers will take the load. Going for the air retrieval mechanism, which is a mechanism that aims to retrieve 1 liter of air at 50 kilometers altitude above Earth's surface while deployment of the rocket. The air sample is then to be studied in the laboratory to study its chemical composition, to try to stop the propagation of climate change and global warming phenomena that we are facing nowadays. As you can see, it consists of a ground evacuated air tank, valve fittings, solenoid valve, and hose that connects the outside with the inside. It functions when the altimeter inside the avionics bay, which is the flight computer, sends the signal to the solenoid valve that the rocket reaches 50 kilometers above Earth's surface while deployment of the rocket, and lets the valve open. Air will enter the tank due to the pressure difference. Calculations were done to prove that the air will enter the tank due to just the pressure difference with no outside pumping source. Now I leave you with Basil with the avionics bay and recovery system.
Now with the recovery system was designed with the purpose of recovering the payload safely and using the rocket or mostly most of its components, again, for economical reasons. The recovery system is consistent of several components such as the swivel, the shock core, the suspension lines, and the parachute. And the parachute has a diameter of approximately 5 meters. This was found using an aerodynamic analysis based on the amount of drag force acting on the rocket during descent. And the final component of the recovery system is the ejection piston cylinder mechanism that was designed based on the isotropic expansion of the solid fuel located in this chamber. Upon expansion, it will cause the piston to ejecting the nose cone and the parachute with it, initiating the recovery process. Now, after getting familiar with the complex operations that are taking place during flight, there deemed a need for a control system that can monitor and control all of these operations. This control system is commonly known in the aerodynamic industry as the avionics system. The avionics system is a set of sensors and microcontrollers that work in integration with each other to perform a set of series of tasks and operations. As you can see, it's located in the avionics bay. It's divided into four different zones. The redundancy zone, where extra microcontrollers and sensors can be added to the system. The documentation zone, that houses a GoPro housing that will document the entire flight. A battery zone that was designed based on the heat transfer analysis to keep the compartment of the battery within operating temperature. And a central zone that houses the central circuitry. The circuitry was designed for a closed loop feedback control system that depends on 6 sensors that temperature, humidity, acceleration, pressure, gyroscope, and magnetic field send serial analog data to the Arduino. The Arduino performs 2 functions. One function is to send backup data to the Raspberry Pi, and the other function is to operate the air retrieval mechanism, the solenoid valve, open it and close it at the predefined altitude of 50 kilometers, and to ignite the nichrome wire in the ejection mechanism to commence the recovery process. Now I leave you with Isa on the fins.
And now for the fins. The fins play a crucial role in maintaining the stability of rocket throughout the flight by increasing distance between center of pressure and center of gravity. And this is due to the increased surface area and lowering center of geometry. So during the flight of the rocket, it may face an inclination angle. So a lift force will be acting on the center of pressure that creates a moment around the center of gravity to return the rocket back to its original path. And for the shape of the fin, we chose a tapered subfin due to its high drag reduction and high stability. Now for the fluttering velocity. The fluttering velocity is a velocity at which the fin will fail due to vibrations. So we developed a MATLAB code that calculates the fluttering velocity versus altitude for different fin thicknesses, 5, 6, 7, and 8 millimeter thicknesses. And we chose the 8 millimeter thickness fin because it has the highest minimum fluttering velocity. And to ensure that the fin won't fail due to vibrations, the maximum velocity of the rocket must be lower than the minimum fluttering velocity. So our maximum rocket velocity 1,261 meters per second, which is much lower than 21.1 thousand meters per second, with a factor of safety of 16.8. After that, we inserted the 8 millimeter thickness fin into Open Rocket Simulator, which is a simulator that a program that simulates the rocket and tells if the rocket is stable during the flight or not. So we put the 8 millimeter thickness, and due to many iterations, we found the other parameters of the fin. Then we inserted the whole rocket with the fins on it to calculate the stability of the rocket, and it was 3.94 calibers. A caliber is a unit to measure the stability of a rocket, and it depends on the center of pressure and center of gravity. Now for the fin attachment, we designed an attachment for the fin to be bolted into the bracket, which will be welded into the body of the rocket. And now for the ambition overall design. This is the ambition overall design, having a diameter of 0.19 meters and a total length of 4.88. As you can see here, when we remove the cover, it shows the avionics bay and the air retrieval section. And now the total mass of the rocket, it was 312, which is considered lightweight in comparison with other suborbital rockets. Finally, with the total cost of the ambition rocket, it was 3,263 Kuwaiti dinars, which is much lower than the average price, which is 20,000 Kuwaiti dinars, according to NASA Rocketry Handbook. And thus, the objective of having a cost-effective suborbital rocket has been successfully met. So now with the safety zone.
So various safety analyses were conducted on the rocket to assure the safe flight and the safety of the personnel operating the rocket. The first safety analysis was the safety clear zone. It tells you whether if the rocket would explode on the launch rail, what is the minimum distance that you should be away from. This analysis was based on the Federal Aviation Administration and the U.S. Department of Defense. We assumed that the entire propellant acts as TNT, and upon explosion it would give a peak incident overpressure distance of 101 meters. That means the pressure at that distance would be safe for humans to be. The hazard fragment distance is 366 meters, and that means the sharpnel and the metal of the rocket, if it explodes, wouldn't be in high velocities to harm any person standing there. Taking a factor of safety of 3 gives us a distance of 1,100 meters as a radius of the safety clear zone. Another analysis done was the landing zone of the rocket. It was based on a 4.9 meter parachute, as discussed by Basil, with a drag coefficient of 2.2. We chose a descent rate of 7.6, which is recommended by the NACA rocketry website, and an ejection altitude of 40 kilometers. This gave us a diameter of the landing zone of 10 kilometers. So you can see here at the Google Earth video, it shows the landing zone of the rocket. This circle is 10 kilometers in diameter, and we assume the launch happens in the center of the circle at Adera launch range, which is used for military exercises and launches. So it's a good range within the Adera range. It doesn't go out to other areas. So the Ambition rocket is quite large, 4 meters in height, and it would take a lot of time to build and present here in the timeline of the course. We went ahead and built a prototype rocket, the Pioneer. Pioneer is a small solid rocket engine rocket that flies up to 500 meters. It has a length of 1.37 meters and it's scaled down by 3.5. It tests the similar components and methodologies of the large rocket, but on a smaller scale that can be tested. Now we can see the specs of the rocket. It has a total propellant mass of 2.77 kilograms based on potassium nitrate and sugar, and also with a total launch mass of 21 kilogram and a flight time of 88 seconds. It reached apogee at 15 seconds, which is the max distance of the rocket. So to validate our design of Pioneer, we conducted various tests to see if it would work upon flight, and here are the tests. The first is an engine verification. So we utilized a similar engine that was flown before, a year ago, called the Ambition 1 engine. It's based on a small rocket, and it's verified. This is the launch video. It went to a max distance of 1,300 meters. And performed as analyzed. So this is the engine here retrieved, and it was able to sustain the combustion pressures, and was chosen and refurbished to be used on Pioneer. Another test is the ejection testing of the parachute. So in order to retrieve the rocket, we'd have to eject the parachute outside of it at the apogee, which is the max distance of the rocket. The parachute is housed inside the nose cone, and we tested here whether our designed ejection mechanism, similar to the Ambition large rocket, would work as designed. So it has a solid propellant segment that's inserted in the piston sleeve, and upon ignition with a heating element, it would combust and push the piston out. And this is the video here of the test. And you can see we did this in many iterations. It worked fine. It pushed the nose cone outside of the rocket, and this will happen at 15 seconds at apogee. Another test conducted was a parachute test of this parachute here. We previously tested this parachute on speeds up to 100 kilometers per hour. This simulates the rocket when it's descending, and would let us know if the shrouds and cavalry ropes would be able to sustain the forces on the parachute, or it would tear. It worked fine, and it took the forces and high velocities of that. And now I leave you again with Mohammed to talk about the flight simulation.
Going for the flight analysis of Pioneer rocket, we did simulate the flight path of Pioneer rocket using a RockSim program, which is a program that is used to simulate the suborbital flights. It gives the maximum altitude, it gives the flight trajectory, and it gives when the parachute will be deployed. The maximum altitude was simulated to be 238 meters, which is due to the maximum load that the program can take of the fuel. We used for the program, we used just half of the fuel, but for the MATLAB code verification, for the full amount of fuel of the rocket, it will reach 500 meters. Going for the video, here we have a zoomed in picture of the video of the rocket, and here we have the flight path of the rocket. As you can see here, the parachute is deployed after the apogee by 5 seconds when the rocket is tilted by 45 degrees. It will continue its path. Going for the fuel of the rocket. We cooked the fuel of the rocket ourselves. We did 9 tests for different composition and proportions of the fuel to test and choose between them in order of the burn rate and the cooking time. Test 4 was chosen to be the best test in terms of the cooking time and the burn rate. It gives the fastest burn rate and the shortest cooking time. We made 10 batches, 10 fuel segments of the fuel, which consists of 66% potassium nitrate, 34% of sugar, and 10 grams of water for each 100 grams of propellant. The 10 segments will ensure that the rocket will reach a 500 meters simulated using a MATLAB code. Going for the ignition test. We did an ignition test to test one of the fuel segments, to test its burn rate. The wireless system consists of a transmitter, receiver, nichrome wire, and the fuel segment that's being tested. Once the transmitter sends the signal to the receiver, it flows a current into the nichrome wire, which has an extremely high friction, which will cause the nichrome wire to heat up and ignite the fuel segment. Here we have the video shows the ignition test. Here we are setting up the system. This is the transmitter, and the fuel segments is 150 meters away from us for safety reasons. It is now ignited successfully, and the video was zoomed in this moment. Now going for ESA for the air retrieval test.
Now, to ensure that the retrieval test would work efficiently during the flight of the rocket, we did a ground test using a vacuum pump, air tank, hose, solenoid valve, vacuum gauge, and a battery. Jumping on to the video. We will start our test by removing the cap of the tank. Then we will insert the tank of the pump, the hose of the pump. After that, we will turn on the vacuum pump to evacuate the air tank. As you can see, the pressure gauge is giving a minus reading, which means that the tank is now evacuated. After that, we will close the tank to ensure that it will still be evacuated, as you can see now. And then we will remove the hose of the pump. After that, we will insert the cap again, and we will open the tank, as you can see now. Finally, the pressure gauge is giving a minus reading, which means the tank is still evacuated. And the final step is to link the solenoid valve to the battery to let the air flow from the bottle to the tank. And now the bottle is crushed, which means the air has flown successfully from the bottle to the tank.
Now with the final test, for the avionics system, we actually wanted to test out 2 different modules. The first module was for a flight module used in the Pioneer rocket, and the other module was the atmospheric module used in the Ambition rocket. For the flight module, we wanted to ensure that it was able to ignite the solid propellant fuel to commence the recovery system. So as you can see in the video, we used the 8 gust of thrust This simulated the launch phase of the rocket. Now, as it is ascending, it is taking in data such as altitude, pressure, orientation, magnetic field, everything. Now, we are currently, will shortly reach apogee. Yeah, it's ignited. So this proves that the microcontroller is able to perform as expected. The second avionics test was done on the atmospheric module. Atmospheric module, the aim was to get back data to make plots of the temperature, pressure, and humidity gradients of the atmosphere. So we used the same drone again, but this time the ascent rate was much slower to simulate the descent rate of the rocket for more accurate data. Yeah, as you can see, the ascent rate is much lower than the previous test. So it returned back data. It was put into an Excel sheet to give back, as expected, the relative humidity, temperature, and pressure, which were coexistent with the weather temperatures on that day. Thank you. I will leave you with Nasser.
In the upcoming weeks, we will be launching Pioneer at the Adera launch range. We're currently awaiting permits from the Ministry of Defense to have our first proof of concept and flight, and to test the full subsystems and systems of the rocket together. In the end, I want to thank Dr. Mohammed Al-Faris for his amazing insight and valuable information and lessons throughout the project. I would like to also thank Exceed Ghanem for their sponsorship and their trust in our abilities. And I would like to thank Salman Faith for his guidance throughout the project. This project taught us many things: to be determined, self-reliant, and most of all, ambitious. Thanks for listening.
Thank you.